Hey everybody, Dr. Retzik back with you again. This is our 8th video in Honors Calc 4 and is all about the introduction to section 14.5. 14.5 is all about what are called directional derivatives. So we're going to study directional derivatives here in 14.5. The good news is you've already studied a couple specific directional derivatives, namely what you have been calling the partial derivatives. So the x partial, that's the directional derivative purely in the x direction. The y partial, that's the directional derivative purely in the y direction. But you don't have to walk in those directions particularly. You could go hiking any direction you like. So it's all about that same picture. So it's our classic. You got a nice surface. This is meant to be a picture of z equals f of xy. And you can imagine this is sitting in three-dimensional space, maybe like this. There's the z-axis, y-axis, x-axis, like so. And you might be interested in the slope of your surface at a certain point, say at this point here. Now that point will correspond to some input down here, say the point x naught, y naught. And you've seen that if you hike on a path where x changes and y is held fixed, like this, you will encounter a certain slope. So that's for a hiker going like this. Or if you walk on a path where the y changes and the x stays fixed, you will encounter a certain slope, and that's for a hiker walking like this. But again, you don't have to walk in those directions. You could walk in some arbitrary direction, like northeast. So consider this blue path. What if the hiker was walking like this? So here they are, and they're on a totally different trail. Like so. You might wish to measure their slope on that blue path, just as you have already had success on the green and red paths. The idea is to look down in the XY plane and think about the actual directions that these hikers are walking. So for example, on the green path, our hiker is walking in that direction. And on the red path, our hiker is walking in this direction. And on the blue path, our hiker is walking, say, in that direction. And we should give that blue vector a name. Say that blue vector flat in the xy plane is u equals first coordinate u1, second coordinate u2. And while we're at it, let's make sure u is a unit vector pointing in that direction. It's going to simplify our computations. So we're going to insist that the vector u is norm 1. And the question we're asking is, well, what's the slope in that direction? Okay. The way to think about the slope in that direction is to think about it with limits in the same way that you did for partial derivatives. Think back to the partials. You just compute rise over run over smaller and smaller runs. But for the partials, the run is purely in the x or purely in the y. This time, the run is in the blue direction. So you're running a little in x and a little in y. And so the limit that's important to us in 14.5 is the limit as h goes to 0, f of, okay, it's going to be x naught plus a little bit in the u1 comma y naught plus a little bit of u2, take away f right at x naught, y naught. So that's rise, that's the numerator. And then the run, like always, is h. So you're computing these rise over runs and taking the limit as the run goes to 0. It's just now the rise is computed in the direction of the blue vector, not purely in the red or purely in the green. The notation, okay, capital D for derivative. Subscript vector u, because that's the direction in which we're interested in the slope. This is the thing you're doing to the function f, and it's all happening at the point x naught, y naught. So that's the definition. And this thing, this quantity that you're computing, this object right here, this is called the directional derivative. That's the term we're computing. This is the directional derivative. Notice, if the blue vector had been the vector 1, 0, then we'd be talking about the green path. And if the blue vector had been the vector 0, 1, then we'd be talking about the red path. So truly, the partial derivatives, they really are special cases of the directional derivatives for when you're walking purely in the x or purely in the y. Now we're just broadening our horizons. We can walk in any old direction we please. Okay, that's the picture. This is what you're adding to your sense of what partial derivatives mean geometrically to broach this new subject of directional derivatives. Now, I recall that when we learned about partial derivatives, we wrote down the limit definition, but then we said to ourselves, you know what? This isn't typically the way you're going to compute a partial derivative. To compute a partial derivative, just pretend all the y's are constant and differentiate the way you always do. Okay, so we want something akin to that to help us compute directional derivatives. And the way to figure out what that something is to think along these lines. For slope along blue vector u, let's think of x and y as being restricted to that blue line. So in reality, x is x naught plus multiples t u1, and y is y naught plus multiples tu2. Those are the parametric equations for x and y on that blue line in the xy plane. So when t is 0, you're right at x naught, y naught. When t is 1, you're a full 1 unit in that direction. You've added a full u1, u2. And in general, you're just looking at multiples of that vector u emanating from the point x naught, y naught. Okay, the beauty of this is that now you have these sort of tree diagrams and chain rule comes into play. So the function f depends on x and y for sure. But if we're restricting ourselves to that blue line in the direction of the blue vector, x and y really just depend on t. And so in that sense, f just depends on t. And by chain rule, if you wanted f's regular old derivative with respect to t, then by chain rule that would equal df dx times regular old dx dt plus df dy times regular old dy dt. All right, let's compute these things. So you got df dx. Okay, now look at dx dt. Look right here. The derivative of x with respect to t is nothing other than u1. Likewise, the derivative of y with respect to t is nothing other than u2. And so you see, this is a dot product of the vector whose coordinates are just the partials, the good old-fashioned section 14.3 partials. Dotted with the vector whose coordinates are u1 and u2. Okay, but these vectors have names. This vector here, this is called the gradient for the function f, and it's written this way. So you put that funny upside down triangle like that, and that's read gradient f. Meanwhile, this vector u1, u2, look back at the picture. That had a name in this discussion already. That is nothing other than the vector u. So really, to compute this slope for your function f as you walk along that blue vector in the xy plane, all you do is take the gradient and dot it with the direction vector. Now on the left-hand side of the equal sign, this df dt, that's the slope as you move in the direction of the blue vector. And we had a name for that. That is nothing other than the directional derivative in the direction u of the function f. So that's just u. That's called the gradient. You just dot them together, and this is absolute gold. This box is the big prize in today's discussion. If you want to know the slope in a certain direction, you simply dot the gradient with the unit vector in that direction. So that's where we are at the moment. We want this to translate into computational success. So imagine you had this example. This is reminiscent of some of the suggested problems. If you had an example like this, where they said, all right, let f of xy equal x squared e raised to the xy. So that's a perfectly reasonable function of two variables. And then they said, all right, let u be the unit vector, say 1 over root 2, comma 1 over root 2. So if you're thinking about the xy plane, that's this vector here. X, y, and the role of the u in this example is that blue vector right there. So that's a picture of what's happening in the domain. If the question is to compute let's go black. If the question is to compute the directional derivative for our function in the direction of that blue vector u, then according to the green box right here, all we have to do is write down the gradient Okay, the gradient is just a vector that has as its coordinates the partials. So here's your formula. You guys are really good at partials at this point. Let's take the partial derivative of that with respect to x. This is a product rule thing, so it's derivative of the first times the second plus first times derivative of the second. So yx squared e to the xy. So that first entry is just df dx. The second entry is the partial with respect to y, which is just x cubed e to the xy. So there's the gradient, and then we just have to dot it. With the vector u. So this piece right here, that's the gradient. This piece right here, that's just u. All right, and therefore, if you do the dot product, just like old school Calc 3 style, do the dot product. So you got 1 over root 2 times that first entry, 2x e to the xy, plus yx squared e to the xy, and then plus 1 over root 2 x cubed e to the xy. There's your directional derivative in the direction of the vector u. And if they wanted it at a certain point, like let's say they wanted it at the point 1, 2. So the slope specifically at the point 1, 2, everywhere you see an x, you put a 1. And everywhere you see a y, you put a 2. So let's see if I can do this. Everywhere you see an x, you put a 1. Everywhere you see a y, you put a 2. So this piece, 2e squared plus 2e squared. So 4e squared total. Plus, now this piece, everywhere you see an x, you put a 1. Everywhere you see a y, you put a 2. So that's just e squared. So grand total, book's answer would probably be 5e squared over root 2. E is about 2.7. So e squared is, I don't know, 8-ish. 5 times 8 is 40-ish. Divided by 1.5. So 40 over 1.5. So 40 over 3 halves. 40 times 2/3. I don't know, 28-ish. So the slope's 28. Pretty steep, actually. That doesn't surprise me because there's an exponential, so I bet this flying carpet, this surface, is awfully steep when you're all the way out at 1, 2. Anyway, 99 times out of 100, to compute a directional derivative, you're not going to use the limit definition. You're simply going to take the gradient and dot it with the direction vector. If you have some kind of weird piecewise defined function or a function that is otherwise behaved poorly at a certain point, you might be relegated to using the limit definition. All right, practice. This ought to get you through around, I don't know, problem 22. There's no typo. The problems for tonight are the same as the problems for tomorrow night. We have a whole nother day of discussion to make sure directional derivatives feel good. So for now, make sure the computational facility is there. We'll look at some of the geometric consequences next time. All right, see you soon.